Good morning. Rogini College of Engineering and Technology, accredited with A plus grade by NAC, Department of Civil Engineering, CE 3402, Strength of Materials, Regulation 2021. A. Anand, Assistant Professor, Department of Civil Engineering. So today we are going to see about the thin cylinders. So introduction: the vessels such as boiler, compressed air receivers, etc., are of cylindrical and spherical forms. These vessels are generally used for storing fluids under pressure. The walls of such vessels are thin as compared to their diameters. If the thickness of the wall of the cylindrical vessels is less than 1 divided by 15 or to 1 divided by 20 of its internal diameter, the cylindrical vessel is known as thin cylinder. In case of thin cylinders, the stress distribution is assumed uniform over the thickness of the wall. So thin cylindrical vessel subjected to an internal pressure. Let's D is internal diameter, T is thickness, P is internal pressure, L is length of the cylinder. So this is the image one of the internal pressure P. The cylindrical vessels may fail by splitting up in any one of two ways. The force due to pressure of the fluid acting vertically upward and downward on the thin cylinder tends to burst the cylinder. Stresses in a thin cylindrical vessel subjected to internal pressure. When a thin cylinder vessel is subjected to internal fluid pressure, the stresses in the wall of the cylinder on the cross-sectional along the axis and the cross-sectional perpendicular to the axis are set up. These stresses are tensile and are known as circumferential stress, that is Cope stress, and second one is longitudinal stress. The name of the stress is given according to the direction in which stress is acting. The stress acting along the circumferential cylinder is called circumferential stress. The circumferential stress is also known as Cope stress. The stress set up in is circumferential stress, whereas the stress set up in its longitudinal stress. And here the expression for longitudinal stress. Consider a thin vessel subjected to internal fluid pressure. The longitudinal stress will be set up in the material of the cylinder if the bursting of the cylinder take place along the section AB. So this is the diagram shows the longitudinal stress developed in the material is obtained as, let P is internal pressure, D is the internal diameter, and T is thickness, and sigma is longitudinal stress in the material. So thus bursting will take place if the force due to fluid pressure acting on the end of the cylinder is more than the resistant force due to longitudinal stress developed in the material. In this limiting case, both the forces should be equal. Forces due to fluid pressure is equal to P into area on which P is acting, that is P into pi d square by 4. And resisting force is equal to sigma into area on which sigma 2 is acting. The formula sigma into pi d into t. Finally, you are getting the sigma 2 is equal to Pd divided by 4t. Force due to fluid pressure. And the stress sigma 2 is also tensile. Equations can be written as sigma 2 is equal to Pd divided by 4t. That is longitudinal stress is equal to half of circumferential stress. Thank you.